Okay, guys, welcome. Today I'm going to continue on memory structure and virtual memory topic. We'll follow paging, segmentation topic that we do on this chapter. As you remember from the previous lecture, paging is an important part of memory paging, is an important part of operating systems and memory management. When we talk about paging, I'm not talking about virtual memory. It's more related to which program is located in which part of the memory. That is the original reason. Because programs are compiled into machine code so that machine code contains certain addresses, and those addresses must be in the memory. Then your computer can execute those code from the memory. Unfortunately, when we have multiple programs, each program competes with others to capture the desired position in the memory. Assume that you are executing 2 copies of the same program. If the executable code is assembled into a fixed address binding, fixed addresses assembly code, which is usually the case, they will expect to use same memory location. But unfortunately, we have 2 applications. So the question is how to organize this. The solution is to put memory management unit between memory and CPU. That is what you are seeing on the screen right now. Part of the memory management unit. Memory management unit tells lies. You are asking for the apartment janitor, apartman görevlisi, to buy a bread from the grocery at the corner. He says yes, but actually he buys the bread from another grocery. He brings it back as if nothing has happened. You are happy. He is happy. The bread is taken from another grocery. Another grocery is also happy. So memory manager actually acts as an intermediary between memory, between physical memory and the CPU. Therefore, it changes the addresses. It changes the addresses so that different copies of the same program or different copies of the different programs can coexist in the memory. First solution is segmentation. In the segmentation, each program is separated into different segments, such as first part of the program, second part of the program, editor part of the program, printer drivers part of the program. So segments that are probably running at the same time when you are executing a program. For example, when you are making an image processing software, sharpening image processing routines are usually run at once because of the structure of the task. But printing or compressing or exporting to different file formats may be necessary at different times. Therefore, they might be located in different segments. Therefore, a program may be divided into multiple segments, and each segment have a segment descriptor. We will store which segment is at what location, as if it was multiple programs. So we can distribute those segments in different places in the memory. That will allow us to use the memory a little bit more efficient than the previous case. In the previous case, without segmentation, remember the old example that I have given to you. We have a restaurant. And we have customers coming. As soon as you go into restaurant, one person sits here, another 2 people sits here, another person sits here, another 3 people sit here. So this is kind of inefficient. When you have a segmentation, that means you are grouping friends. You are grouping friends so that they don't look for a contiguous. Instead of having 6 people table, because they talk to each other, they are closer friends, they can talk to each other, they will talk to each other even if they are on the same table, because they are friends, they run together. Therefore, the operating system puts them in different places. That is called as segmentation. So a big executable code can be divided into segments where those segments are closely related to each other. Therefore, we don't look for big tables. We can look for smaller tables, but still these segments have no standard sizes. Some of them could be big. They talk to each other, but they are big. Therefore, you need to store segment length and segment base, meaning how many and who, and which table you are putting those groups. That is kind of efficient, but not as wide. With the paging, these groups have fixed sizes. You have fixed size tables. you have fixed size tables, and the group assume that these are people. The group is divided into standard chunks. Standard chunks. These are called as pages. These are called as frames. And this is memory. Memory is equivalent to a restaurant, and each table can accommodate actually 3 here. Each table can accommodate 3 people. The sizes should match. However, if you have a group of 1 person, he will be alone. And the whole table will be dedicated to him, causing internal fragmentation. There is internal fragmentation, meaning that table is reserved, but our page size is not, customer size, group size is less than, group size is less than the available frame size, available table size. That happens when you are recording on hard drives as well. For example, assume that you have a file with 1 character. What is the length of the file? Usually this big, or depending on the hard drive size, you may see these numbers and kilobytes, sometimes bytes. That's bytes, pardon. Bytes. You are recording 1 character, but it is occupying 8 kilobytes. Because the minimum available table size in the disk drives are 8 kilobytes due to paging structure on the hard drive. So it is a similar structure, but it is not memory paging. So keep that in mind. So this kind of paging avoids external fragmentation, meaning that tables in the restaurants can be filled without any problems, because it is all divided. In the segmentation case, you have tables of different sizes. At the beginning, you have no limitation. It is like you have a long table and seats. If group of 6 person comes, you allow them to sit like this. 18 person comes, okay, they sit as the next group. So this is the first group, this is the second group, and this group finishes, this group becomes empty. Then another 18 person comes. The waiter says, we don't have place to sit you. Why? because this place can take 16 people. This place can take 6 people. But there are 18 customers as a group, as a single program together. So you cannot have them sit. That is called as external fragmentation. So segmentation causes segmentation or locating programs without segmentation as a whole. This is usually the same, but segmentation has less that kind of effect because groups are smaller. That is external segmentation, and it causes inefficient use of memory and usually failures to load even if there is enough memory. So at the end, you will need more physical memory in order to get the same kind of performance or same kind of behavior with the segmentation or without segmentation, because there is external fragmentation. External fragmentation means no tables to sit that kind of group. In the paging, we say groups are divided. So this is a military base, groups are divided. You don't sit together. You can only sit in groups of 3 or groups of 4 or groups of 5 or 6, whatever. Page size is determined by the architecture. So that is the question, that is the idea we said last time. And CPU, memory management unit, and memory. So CPU passes the address to read and write. Memory management unit translates the address. Because memory management unit needs to use the memory efficiently and without giving any information to the application program. Application program should think that everything is working fine. You are getting bread from the corner grocery store, so that it will be happy. Furthermore, when you have big memory as 2 chips, such as this is DIMM1, this is DIMM2, this is, for example, 8 GB, this is another 8 GB, 2 different chips of 8 GB banks. The memory management unit works in conjunction with the chip enable ports of the memories, so that when your total demand, if total demand is less than 8 GB, turn off DIMM2. Even if the program believes that it is working at high address somewhere, memory management unit puts those data in chip 1 and turns off chip 2. The recent memory manager units are able to turn on and off different chips so that it saves power in mobile computers when you have multiple chips or multiple segments of the memory. That kind of turning on and off is also being done in microprocessors. with different cores. Cores can shut them off if they are not required. So equivalent sizes are used. Let me show it this way. CPU puts the address, and address has certain first part. For example, when you have, if this is an 8-bit address, let's divide that 2 by 6. That means 2 means 4 pages. It could be 00, 01, 10, 11. And the rest, how many? 2 to the 6, 64. So each of them has 64 bytes. So that means this is quite unrealistic, theoretical. Normally it is much more. 64 bytes of code or data in page 0. Another 64 byte, another 64 byte, another 64 byte. In the real memory, you have 4 frames, total 256 bytes. Say, this is frame 1, this is frame 2, this is frame 3, the frame 4. And in the logical memory map, this is logical. Again, 256 bytes. This is A, this is B, this is C and D, different parts. So the program believes that now it is program counter. Program counter shows B something, such as, what is B here? 01. So address that goes out from the CPU is something like 01, 0, 11, 01, 0. This is the address. So goes out from here, but the memory chip sees that it is 01, looks at the table. 01 is the distance, and F says 10. Or let's say 11. So that part is replaced. So in this side, 1101 1010 is fed to memory chip, and that corresponds to this location rather than this location. So your program believes that it is working in that area, but actually it is in a different area of the memory. In terms of addressing, in terms of the addresses that happens in the that occurs in the program, program doesn't know anything. It still thinks that it is working in that location. Also, program counters and stack pointers or whatever, they are all in location B. The location translation from location B to F3 is done by memory management unit for each memory access. Since it is done for each memory access, it has to be very fast. Therefore, it is done using hardware circuit in no time. Any questions? So this is what I have done with different size of logical memory and physical memory. In here we have 8 frames and 4 pages. What the sizes are? Size of one page is equal to size of one frame. So sizes must be equal. In the page table, I keep the association, and whenever I need to access to memory, I look at the page table. That is that's another example. This is from the book. how much fragmentation can happen when you have, for example, 2K pages, and when you have 72K program size or process size, it will occupy, just divide this into two, divide this into one of another. It will take 35 pages plus 1000 bytes. Therefore, 962 bytes are not used, and it goes into internal fragmentation. When you have very small programs running, compared to page size, that means internal fragmentation will be significant. Significance is increased. In worst case, when you have one frame contained by 1 byte, as I said, 1 character, the only 1 byte is used in the frame. The less, which is 2047, will not be used. If we have small, in order to reduce that, people may think that small pages are good. On the other hand, there is a page table. If you have small pages, your page table is bigger. So searching which page, calculating which page becomes very hard, and it actually becomes impossible for small pages. So there are strategies to deal with that. Some architectures use multi-level pages. Some architectures, like Solaris, has different sizes of pages. Some architectures have pages and paging and segmentation together. So if it is necessary, if it is good enough for paging, it switches to paging at the same time. If the block is very big, treat it as segmentation. So they try to reduce number of pages that needs to be tracked by the hardware, because hardware size becomes very big. Normally, page table is stored like this. When new processes come, page table is updated. Page table is updated, and free frame list is also updated. Page becomes allocated. Sometimes page table needs to have the base in the memory, in the main memory, and page table has the end, so it has the size in the operating system. But if we store page table in memory, even in somewhere else, a fixed location, every data instruction or instruction access, every data or instruction requires 2 memory accesses. One to find the location of the memory. So memory slowdown will be twice. So memory speed will be halved. Therefore, we use associative memory, named as translation look-aside buffer, which is zero-time lookup register, zero-time lookup memory for finding which page is located in which frame. That's in memory. Using translation look-aside buffer, for processes, it is very interesting that that buffers must be manipulated cleverly. Otherwise, at every context switch between task switching from process 1 to process 2, those buffers must be refreshed. So in order to prevent that, translation look-aside buffers also store information like process IDs and information relevant to which process is running now. So automatically can switch between which process that I am dealing with and check base and limit registers as well, depending on the process ID. Obviously, we cannot put everything into translation look-aside buffer. It's a statistical kind of memory. It's like a cache. Sometimes there is miss. If there is a miss, then we have to look at the main page table. Furthermore, some system-related entries can be wired down for permanent accesses. So for certain architectural locations, those locations in the memory, such as vectors, interrupt service routines, etc., those entries can be wired down depending on the architecture. Any questions? So this is like database. When you enter page number, the chip, you enter page number, it goes out frame number in 0 time. So there is a gate network inside, like FPGA. It can automatically gives out the frame number. So when you connect that to memory management unit, it can compute the relevant frame number in no time. This is the final architecture we are dealing with. So there is a translation look-aside buffer. This translation look-aside buffer is first checked if you can find what you are looking for, the frame number inside the page number, inside the translation look-aside buffer. Then you replace the first part. If not, you refer to the page table in memory, but this requires interrupt service routine to work, so it is kind of very slow. It should happen once in 1,000 or once in 10,000 or more, once in 1,000,000 or something. This is one important effective access time calculation. Normally, we can tolerate like 10% of access, 10% of the memory access time for the as an epsilon maximum. So if you have, for example, 60 nanosecond access time memory, 6 nanosecond delay can be tolerated by the associative memory. So that is epsilon. Hit ratio means what percent of the page numbers are found in the registers. So if you can find the desired page in the buffer, the time you need is 6 nanosecond. If not, you need to look at the page table, which will require multiple memory accesses. Here it is 100 nanoseconds. So in the book, you have 100 nanosecond and 10 nanosecond. Memory access requires 100 nanosecond. Additionally, 100 nanosecond for memory access is required all the time. This 100 nanosecond is required for additional access to check page table. Therefore, how much time is required with 80% hit ratio and 20 nanosecond for search? It is probability times this. There is one access with single probability, 2 accesses with the remaining probability and updating, not updating, but checking and not finding, and updating the translation local set buffer. So if that part is, this part is 2 plus epsilon minus alpha. If alpha is 80% and epsilon is 20 nanosecond, 80 times 100, which is the access time, 20% times 200. That makes 120 nanosecond. So 20% slowdown. Or hit ratio 99%, 20 nanosecond for search. 99 times 100, 0.1 times 200. Then it means 101 nanoseconds, so 1% increase. Therefore, it does not slow down twice, it slows down a little bit because of the hit ratio advantage, and epsilon is then negligible. These things are not that easy for memory managers because there are process IDs. And sometimes there are pages, there are frames. When you are doing mapping, and there is a program here, frames must be empty at the beginning. This is A, this is 1. So A will be moved to 1, but at the beginning, memory is not full. Page table may have A corresponds to 1, but the content is not yet there. Or maybe it was there, but currently I should consider it as empty. Therefore, I need a valid invalid bit attached to each entry to page table. It must be valid after copying the content. It must be valid, meaning that page is there and use it from there. If there is an invalid bit, which is 0, invalid bit is there, the content of this location in the real memory means currently it is empty. When the memory is empty, we don't delete the content, we just ignore it. For that reason, if it is considered as empty, we say it is invalid. Or if it is dirty sometimes, then we say it is invalid. If it is fine, consistent with the actual need, then we say valid is 1. If any problems occur, we generate software interrupt and we solve the problem with probably with low probability. We solve the problem from time to time. So any questions? I keep asking any questions, but nobody is asking questions. Nobody is shaking heads. Nobody is saying yes. So I'm not sure if you are there or not. This valid bit example shows frames 6 and 7 is invalid, meaning that page 0 is located here. Page 0 is located in 2. Page 1 is located in 3. Page 2 is located in 4. Page 3 is located in 7. Page 4 is located in 8. Page 5 is located in 9. Page 6, there are no page 6, so it is invalid. Those spaces are empty. If I have random things here, then invalid bits allow me to say there is nothing there. Only these are defined. Or if I drop this page from memory, I simply switch this invalid. When it is invalid, it is kind of, it becomes empty and can be used later. Paging allows us to do more. One is shared code. If the code is read-only, that can be shared among multiple processes. That part of the code can be shared. So some pages are read-only code. That kind of code is called as reentrant code. Those pages can be shared. It could be printer driver, it could be an editor, it could be image processing application, it could be a web service. So many parts of many programs, if multiple instances are running, like servers, contain shared codes. So rather than occupying same code in different places in the memory, if the code is read-only, I can share the page. So memory manager can also help us to share the code of the same instance when it is repeated multiple times, or maybe sometimes sharing between parent and child in thread systems. Furthermore, some of them have private code, and those must be kept separately from each other. Although they are the same program, like editor has private data and private code for local purposes. This is one example on that. you have first editor. No, this is one editor, and editor has four pages. This editor, same editor, 4 pages. A traditional approach will require me to use 8 pages, 8 frames in the memory. But since these are read-only, I can have them shared. So in the process page table for 1, 3461, page table for P2, P3, 3462. This is P2, a third one, 3467. So I have 3 processes, 3 editors working, but only 1, 2, 3, these are shared, and these are private. Therefore, instead of 12 frames, we use 6 frames in this example by code sharing of reentrant codes. That is what reentrant means. When you re-execute the same part of the memory, nothing is changed in that part of the memory. We call that kind of code as a reentrant code. It can be run over and over and over without state changes in the code. We have some examples here. One example shows page size of 4 kilobytes with 32-bit addressing mechanism, and page table would have 1 million entries. If each entry is 4 bytes, 4 megabytes of physical address space for page table is required. So therefore, small page sizes with page tables are not feasible. A lot of memory is required. Therefore, different mechanisms of paging are invented. These are hierarchical paging, hashed paging, and inverted paging. Normally, for example, in hierarchical paging, I have page and frame. In the hierarchical paging, I have P1, P2, and frame. So P1, P2, maybe P3, 3 level, are arranged hierarchically and stored in different subtables. In the hashed page tables, rather than searching, I only store the items that are only used pages, or invalid pages or unused pages. I don't store anything. So that allows me to reduce the page size, the table size. In the inverted page tables, same idea. If they are not used, just store the frames and corresponding pages rather than pages to corresponding frames. So left and right swap the page table and becomes frame table. Let me show them to you. Multiple page tables like this. We have the outer page table and page table. So first, this page is divided into 2. First part is looked here, and the second part is looked here. in this table. So first table is this one, meaning this one. Second table is this one. So this is first table, this is second table. Therefore, the search is quicker, and it will reduce the memory burden generated by single page table, because you generate page table with subtables, and if you don't need that many, you don't generate them. Also, translation look-aside buffers load these as necessary rather than trying to load everything, the whole page table, and that will allow smaller translation look-aside buffers. I mean, acceptable size translation look-aside buffers. A 32-bit example, 12, 10, 10. That's the famous example. This is the first page, outer page and inner page, and then the offset. 2 to the 10 means 1K. 1K page sizes are considered in this architecture. This is also called as forward mapped page table. I have explained this in the outer page table. First part is found, then in the inner page table, if it exists, second part is found, then replaced, and frame is located in the physical memory. In the 64-bit architecture, we have bigger outer page table size, 42-bit for the outer page table, and for the inner page table it is 10, so 1000 to fit into translation look-aside buffers. This is for TLB generally, and this is for 4K memory pages, and this is generally 64-bit architecture that we are seeing today. Again, outer page table has too many entries. It is too big. Even if you have 34, 8, 10, and 12, it will be still big. So the idea is to make this faster. The answer is, this is 3-level example. Outer, inner, offset. Second outer, inner, offset. Again, this is big, then bigger. The question, the solution is hashed page table. Nedir o? Her şeyi yapamıyorsunuz. Bari sadece bana lazım olanları hesap edeyim, kaydedeyim. Koca bir table oluşturmayalım. Otoparkın çoğu boş çünkü. Sadece giren arabaların ben düşüneyim şeklinde bir yaklaşım. So hashed page table approach is very common in architectures over 32 bits. So today's architectures are always, unless it's a small microprocessor, it is bigger than 32 bits. So each element contains virtual page number and the value of the mapped page frame pointer to the next element. The page numbers are compared in this chain searching for the match. Usually it is a hash function. The first one is giving the answer. So it is a high hit ratio. And hash, how long it takes to compute a hash? Evet Tuğcan. Seni görüyorum, sana soracağım. Geldi gitti ses.
İngilizce mi cevap vermem lazım hocam?
Yo, Türkçe olabilir. Hash ne kadar sürer hesaplaması?
Yani uzunluğuna bağlı. Bir de karmaşıklığına bağlı.
Bu şeyde, in this architecture, it will only take 0 time. It will not be computed by the CPU because we are talking about instant access to memory. So we need a hardware to compute hash, like something in, something out. Immediately. So when I expose address from the CPU to the address bus, it should translate the address immediately if it is found in the hashed page table. If not, if the hash function does not hit, then it should go back to interrupt service routine and find the connected one or next one or whatever is necessary. So usually it maps to a correct one. And that is that hit ratio must be over 90% or more. Then most of the memory accesses will not be affected by remapping. Otherwise, if we make computation for every memory access, the system will slow down in an unusable way. Therefore, there is a clustered page table and there are variations. Let me show. This is how it is. There is a hash function, zero time hash function. That zero time hash function immediately selects the address in the local memory, local fast memory. That fast memory immediately extracts the address. That address is replaced. That address is replaced. Unfortunately, it is Q. So the system sees it is not the first one in the hash list, checks the pointer. The second one is the correct one I am looking for. So this is the entry in there replaced with the address bus first part, and memory chip sees this address. I hope I could explain this good enough. Usually it is the first entry. Usually it is the first entry. It is not. If it is not the first entry, some slowdown, further slowdown occurs. This is another old technique. Inverted page table. Instead of assume that you have 64-bit architecture. What is the memory size? Hesaplayalım. It is too big, right? So your logical address space too big. So for let's say 10, inner, outer, 44. Still too many. Do I have this kind of memory? No. What kind of memory I have? I have 8 gigabytes of memory, which is here. Very small. Therefore, inverted page table says, make a table for this part, and in the entry for each frame, store which part of the logical memory is mapped onto. So frame 1, frame 2, frame 3, frame 4, frame 8 gigabyte. Because I have physical memory of that size, that kind of physical memory will map to which logical memories. So if you hold this table instead, if your architecture has big memory, logical memory, but not physical memory, due to address bus and architectural sizes, inverted page table is a good alternative. One entry for each real page in the memory rather than logical page, one entry for logical pages. It decreases the memory needed to store each page table, but increases the time needed to search table.
Hocam bir soru sorabilir miyim?
Tabii sor.
Şimdi bu olay yani physical memory kullanıldığı için hafıza alanı aslında biraz tasarruf sağlanıyor ama şimdi one entry for each real page diyor ya memory'de. Bunun evet. Shared memory şey nasıl olacak? Yani daha shared memory konusunda şey değil gibi sanki. O yönde bir avantajı yok gibi. Çünkü her page table...
Ayrıca hangi proses, doğru söylüyorsun. Hangi prosesler kullanıyor diye bir de onu tutması lazım.
Evet.
Hangi prosesler kullanıyor diye tutması lazım. Gene page sharing yapabilirsin. Çünkü önemli olan hangi frame'in hangi page'de bulunduğunu bulmak. Ama bunda şöyle bir sıkıntı var. The problem is CPU extracts P and D as an address. This is page. What you need to find is you have 1, 2, 3, 4, 5 as the entry. In this mechanism, you need to search for P. In the previous method, you only find the item in location P, which is very fast. In this inverted page mechanism, you need to search for P, where the P is. That is different. So usually hash function is preferred. So rather than linear search, a previously introduced hash page table technique is used for constructing hashed inverted page table. Furthermore, associative memory can be used. And that answers your question, how to implement shared memory. And you need to keep track of, that is answer to your question. You need to keep track of what you share in addition. This is the architecture. As I said, you need to store the process ID as well. So process ID and P together. The item you are found has the ith item. That I is replaced with this first part of the address, and physical address is generated. Therefore, different processes can have different memories. The advantages reduced page table size. It's basically finished. The book gives certain examples from the common systems. Spark Solaris operating systems. Let me show it to you. This has 64-bit operating system, and again, translation look-aside buffer method is used. Intel architectures are 32-bit and currently 64-bit. Let me show that to you. In the Intel architecture, segmentation and paging is used together. There can be 4 gigabytes of segments and 16K segments per processes. So there is a segment table. And 8K segments are private to process. Second partition is generated. Those are shared segments. So global data and local data is separated with this kind of exception. There is a figure I'm going to show. In the 32-bit address, you have S, G, and P segment descriptor. This address is given to paging unit, and paging unit extracts the equivalent frame to real memory. It can have different page sizes between either 4 kilobytes or 4 megabytes. And it therefore preserves the length of the page table. If the page is big, then you have big pages. It is like the restaurant with big tables for big groups and small tables for small groups. So two different sizes of tables. This is 4 kilobytes. This is 4 megabytes. So if big customer comes, big group comes, you put them into big table and treat it as a single entry in the page table. If it's a small group, put them into small frame and keep track of those tables separately. Therefore, number of tables and table IDs and table lists can be reduced significantly. Segmentation and paging together, we said. First, there is segmentation, and within segments, there is paging, then physical memory. So this is how Intel is doing its business. And segment selector, etc. There is a segment index. In that segment index, you find which segment I am in, and then generate the 32-bit address. So that is Intel 32-bit architecture. Paging part. You have page table and hierarchical page directory. Once you find which page table you are interested, then you look for your local location of the page, locate the page, and generate the final address. So first part is the outer page table. This is inner page table. So basically it is multi-level page table. It has it allows apps to access more than 4 gigabytes of memory space. There is a 2 to the 32 limit. Türkçe söyleyeyim de biraz hareketlenin. Limite geldiniz. Diyelim 2 üzeri 32 veya 16 bit. 16 bitlikte limitiniz nedir? 256 kilobayt değil mi? Pardon 64 kilobayt. 64 kilobayt 2 üzeri 16'da. 16 bitlik mimariniz var. 64 kilobayt hafıza olabilir. Ama ya daha fazla istiyorsunuz ama mikro işlemcinizi de çok arttırmak istemiyorsunuz. Ne yaparsınız? 32 bitlik mimariniz var. 4 GB memoride takılıp kalacak mısınız? Ne yapacaksınız? Çözüm şu. Bir tane pointer koyacaksınız. Bir yere bir flag koyacaksınız. Her instruction'da önceki grupta şöyle bir şeyler söyleyeceksiniz. Ben şimdi şurada çalışıyorum diyeceksiniz. Ondan sonra orada çalıştığını varsayacak sistem. Ben şimdi şurada çalışıyorum diyeceksiniz. Sonra orada çalıştığınızı varsayacak sistem. Dolayısıyla blok şu bloktayım, bu bloktayım, bu bloktayım diye mesela 16 kilobayt, 2 üzeri 16, 64 kilobayt. 64 kilobaytlık 4 tane bank koydunuz. Her biri 64. Each of them is 64. So just introduce an instruction indicating which bank you are now. This is bank 0, bank 1, bank 2, bank 3. So tell memory manager that which bank is you are going to work at that particular time. Then follow the instructions after that, and those instructions are executed in bank 0. If you say you are in bank 3, bank 2, then the instructions that comes after that description uses this bank. Therefore, page directory pointer table is invented, and page directory and page table entries moved to 64 bits. So it is actually 64 bits architecture added to 32-bit architecture. Therefore, it is increased to 36-bit of physical memory space in Intel. So 64 gigabytes of physical memory is the limit for Intel 32-bit machines using an additional banking mechanism, directory mechanism. If we divide 64 to 4, 16. So I have 16 of these banks. 16 of these banks in the Intel architecture. So it gives me additional 15 more 4 gigabyte of chunks, selectable chunks. Now, current architecture 2 to the 64 is 16 exabytes, which is big. So they do 48-bit addressing for today's standards. Page sizes are variable, 4 kilobytes, 2 megabytes, 1 gigabyte. So in the restaurant, I have small table, medium table, and big table. 3 types of tables are available in the restaurant. So depending on the customer, I can allocate different page sizes. And hierarchical paging is 4 levels. It is very hard to draw. 4 level. Suyunun suyu şeklinde. Level 4 directory, inner, and final address. So 4 levels of paging is available. This part they didn't use yet. In the ARM, 2 different kinds, 4 kilobytes and 16 kilobyte pages, 1 megabyte and 16 megabyte sections. So this is different kind of restaurant. There are small tables and big tables. Small tables are 4 kilobyte and 16 kilobytes. And big tables are 1 megabyte and 16 megabyte. So 4 types of, because of the needs of the applications. These are the page sizes, and these are called as sections. 1 level paging for sections because they are big. 2 level paging for pages. So for these 2 level pages, these are 1 level pages. Obviously, different page directory. 2 levels of TLBs are available. Outer levels have 2 micro TLBs, one for data, one for instruction. So for the instructions, since they execute one after another, they are probably somewhere else in the memory. So they have different TLBs for data and instruction so that hit ratio can be increased. Usually, data and instructions are in separate locations in the memory during the program execution. Inner one is main TLB. These details I am not very familiar with, but I think you get the point to some degree. 32-bit ARM architecture has inner page table, outer page table, and different page sizes. The memory. Maybe you have some misunderstanding when I am drawing physical memory. These are frames, right? These frames are, these boundaries are virtually determined. These boundaries in reality do not exist. Those boundaries are there because we say them so. Therefore, with this architecture, with ARM architecture, since I am storing where they are, some of them can be small, some of them can be big. This is, for example, 16 megabyte. This is, for example, 1 megabyte. Okay? Actually, 1 megabyte and 16 megabyte. 16 megabyte contains 16 of 1 megabytes in terms of size, but the boundaries do not exist because that's for our understanding. In reality, there are no boundaries. If we say it is 16 megabyte, it is 16 megabyte. Finished. Now I'm going to move into hard drive, backing storage. Sorunuz var mı? Any questions? So virtual memory is different, but very related to memory paging and segmentation. Virtual memory is an integral part of our modern operating systems, except sometimes except embedded certain systems, virtual memory is present. We will talk about page replacement algorithms, trashing, and other considerations now. So probably I'm not going to finish, but I'm just going to introduce. This is CPU. This is my memory. There is memory. And we have hard drive. Disk. Where is my program at the beginning? My program is here. This is my program. Okay, on disk. So if I click on this, what happens? The operating system should put this 1, 2, 3, 4, 5 into memory. First one is the code. This code is loaded to somewhere in the memory. Obviously through here, through memory manager. Yani hangi bakkaldan ekmek alınıyor bilmiyoruz yani. O Onu artık unutun. Bak, ekmek mutlaka bir yerden gelecek. But assume that it is coming from somewhere and the first item is put. Ekmek aldık ama peynir yok. So the next one is cheese. Cheese is also necessary. Bread comes, but cheese is not in the memory. So you ask for that. When you execute cheese, then there are olives. Olives must be brought to memory. So as you execute the program, those parts need to be brought into memory. The strategy is, since we have frames, these blocks from the hard disk or stable storage or flash, whatever, needs to be brought to bring to memory. They need to be brought to memory to work. That happens by interrupts. At each time, ekmek, when you say that hello exe is not here. Where is it? On the disk. Oh, okay, interrupt. Bring the bread, bring the first block. Yes, start executing first block. And at the end of the first block, you try to jump to second block because the code continues. When you try to continue, actually in real memory, it is not here. In real memory, it can be somewhere else. Bak, başka bir bakkalda olabilir yani. But doesn't matter. In the logical memory, this is logical. It is one after another. So in the second block, cheese is not there. Interrupt service routine, bring it from disk, put it in here, and start executing. So anytime you need to execute a code, it must be brought into memory. Block by block, frame by frame. Therefore, code needs to be in memory to execute. But entire program rarely used. Yani bütün bakkalı eve getirmeyin. Sadece yiyeceklerinizi alın. Özellikle ekonomik kriz olduğu zaman çok fazla şey almayın. So, usually, parts like error code, unusual routines, printing issues, there are many parts of code that are not used. So, like here, many part of the code is not used. Only required part can be brought into memory. Furthermore, entire program is not needed at the same time. Although you run at the beginning some part of the code and at the end you run other part of the code. Mesela bakkaldan aldınız, ekmek, peynir, zeytin yediniz, bitti. Sonra tatlı yiyeceksiniz. Tatlıyı sonra yiyebilirsiniz. Aynı anda masada bulunmasına gerek yok. So entire program code not needed at the same time. Although your whole food experience contains multiple things, that food experience considered as a program need not to contain everything on the table at the same time. Some things may stay out for a certain time. Therefore, we should have the ability to execute partially loaded program. That is very important. That is very important for mobile as well. Therefore, program is not constrained by the limits of the physical memory. You can bring certain parts. Öte yandan bakkaldan ekmek al gel. Ekmek ye. Ekmeği buzdolabına kaldır. Peyniri getir bakkaldan. Peyniri masaya koy. Peynir ye. Peyniri buzdolabına kaldır. Ekmeği getir. Ekmeği ye. Tekrar ekmeği götür. Peyniri getir. This is ridiculous. So for certain things, they need to stay together. But for some other things, they may not be required, depending on the program. So only one frame may not be enough. Each program takes less memory while running. Therefore, more program can run at the same time. That increases the memory utilization and CPU utilization. Less I/O is needed to load the program because you have, for example, your hello exe is, let's say, 65 megabyte. But when you start it, you don't have to load this 65 megabytes into memory. You just start loading with 4 megabytes, start running, and continue. This is 65 megabyte of code. The big 4 megabyte of code. Maybe you have a go to somewhere. Go to here. So if you have a go to command to this part, only load the second 4 megabyte. So don't load other parts of the program. So that will reduce input and output requirement as you run the program from disk to memory. But in some cases, if you are a heavy user, if you have guests at home, maybe you will eat a very rich dinner. So when you are eating very rich dinner, you may buy everything from the grocery and bring on the table. But normally, no. In the virtual memory, separation of user logical memory from physical memory was provided from the paging architecture. Furthermore, only part of the program needs to be in memory for execution. This is important. Then it will allow us the fact that logical memory can be much larger than physical memory. Logical part of the memory can be much larger because I don't need it all the time. I don't need it all the time. Address space can be shared by several processes like we have described in half an hour ago. And process creation becomes fast because you don't have to load everything from the beginning. Hani helva yap dediğin zaman adama şeker yok, mutfakta bulaşık makinesi yok diye sormaman lazım. Bulaşık makinesine gerek yok. You don't need dishwasher to make a food. So more programs can run at the same time. Less I/O needed, as we said, is required. That we will be doing next week. If you have any questions, let me know.